The second of the limit interchange theorems is related to the derivative. So if you have a sequence of function fn which converges to f uniformly on some set A, and all of the fn's are differentiable on A, then the limit f is also differentiable on A. So I will represent some closed bounded interval AB. The fn's are functions from I on to R for every n if there exists a point x0 in the interval I such that the sequence of fn at x0s as real numbers converges, and fn is differentiable for every n, and the derivatives converge uniformly to some function g on the interval I, then on the one hand the original sequence of functions converges uniformly to some function f on I, and the derivative of f is actually g. This is a fairly involved statement. Let's see what the proof looks like. Well, what we're going to show is that if these two assumptions are met, then the sequence fn satisfies Cauchy's criteria. And so in particular, the fn's will converge uniformly to some function. Afterwards, we will show that this function derivative is equal to the same limit, uniform limit of the sequence of the derivative at prime. So let epsilon be greater than 0 and x be a point in the interval I. Because by hypothesis, the sequence of derivatives converges uniformly to a function g on I, the sequence fn prime satisfies Cauchy's criteria. In particular, that means that there exists some n1 which only depends on epsilon, such that fn prime at some value of the function, let's call it y, minus fm prime at y will be less than, well, some quantity, any positive quantity we want. So I'll take here epsilon, which was given by my initial choice, divided by twice b minus a. This is also a positive value because the interval AB here is not a singleton. This is true whenever n and m are greater than n1 and y is some point in the interval I. Now, without loss of generality, let's assume that the m's are greater than n, and if it's the other way around, we just relabel the indices. We know that fn at x0 converges. It's a sequence of real numbers which converges, so it also satisfies the Cauchy criterion for sequences of real numbers. It's not quite the same Cauchy criterion, right? Because it's a Cauchy criterion about sequences of numbers as opposed to sequences of functions, but it's basically the same result. We're just working with different objects. What this means is that there's some index n2 such that fm at the specific point x0 of interest minus fn at the same point is going to be smaller than epsilon over 2, remember, and m greater than 2. And as before, I can assume or arrange for m to be greater than n. Okay, so now I use the mean value theorem, which tells me that there's some point y between x and x0 such that fmx minus fnx, that's one function, minus fm at x0 minus fn at x0 is going to be equal to fm prime at y minus fn prime at y times x minus x0, right? Or if you want to just not get confused by the choice, think of this as b at x, think of this as b at x0, think of this as b prime at y, what we called c, and then this is just x minus x0, and then that has the form that you come to expect of the mean value theorem. In particular, what this means, if you look at the distance between fmx and fnx, that would be less than or equal the distance between fmx0 minus nx0 plus the distance between fm prime y minus fm prime at y times x minus x0 in absolute value. So all I've done here is I've taken this component here, sent it to this side by adding it to both sides of the equation. Then I take the absolute value of what's on the left, and I use the triangle inequality, what's on the right. Now this first little bit, fm at x0 minus fn at x0, we know that this is smaller than epsilon over 2 because the sequence fn at x0 is a Cauchy sequence, and so we can find appropriate threshold n2 so that whenever m and n are greater than n2, this distance here is smaller than epsilon over 2. The distance fm prime y minus fn prime y, that is smaller than, by assumption that the sequence of fn primes converge uniformly to some function g, epsilon twice e minus a. And the distance between x and x0, well, x and x0 are both taken within the interval I, and so you don't have a choice. Their distance is at most equal to b minus a, which is epsilon whenever m is greater than n, greater than, say, the maximum of whatever n1 and n2 were, because there's no guarantee that the threshold n1, whose existence we know thanks to the fact that the fn primes are converging uniformly to g for a given epsilon, and n2, whose existence is given by the fact that fn x0 is a Cauchy sequence, or it might not be the same. So we'll just pick the largest of the two, in which case both of the inequalities that we found be valid, this one for n2, the other one for n1, and that leaves us with the proof that this sequence is a Cauchy sequence. Now there's one niggling detail here. We are using x. Do we know for a fact that n1 and n2 are not defined, not dependent on the value of x that we've selected? Let's back it up a bit. What happens at x0 is independent of what happens at x. So this is true only for the Cauchy sequence fn at x0. So this n2 here is not dependent on x. This is why we have this weird assumption to start. The second one, the n1, well, we know that the convergence of the fn prime is uniform, and by definition that means that it doesn't matter what value we pick here. So what we do have, n1 independent of x, n2 independent of x. X is completely arbitrary, so this choice here is independent of x, and so by Cauchy's criterion we have that fn and n converges uniformly to some function f. At this point we don't quite know what it is on I. Now, we don't know what it is, but whatever function that is, whose existence is proven by Cauchy's criterion, we will show that its derivative is actually equal to g. And we'll be done. So let epsilon be some arbitrary positive number. Let's see, belong to I. Because the fn primes satisfy Cauchy's criterion, we know that there exists an integer k, an integer k1. I'll specify here that this is independent of y, which will be the variable that I will use later, such that fm prime y minus fn prime y will be less than epsilon over 3 whenever m greater than n greater than k1 and y at some point in the interval I. We know that the limit of the fn prime at c is equal to g at c. That's in the statement of the theorem, which means that you can find some integer k2 such that fn prime at c minus g at c will be smaller than epsilon over 3 whenever n is greater than k2. Set k to be the maximum of both of these values, so that now whenever m or n are greater than k, they'll both be greater than k1 and k2 simultaneously. Since if k prime at c exists, because the functions are all differentiable, you can find for that specific epsilon greater than 0, then we started the second half of the proof with a delta epsilon, also positive, such that the difference between the difference quotient fkx minus fkc divided by x minus c minus f prime at c smaller than epsilon over 3. Fk prime at c is smaller than epsilon. That's true whenever x minus c is smaller than delta epsilon and x is in the interval a. Okay, let's all put this together. We use the mean value theorem again to show that there exists a y between x and c such that fm at x minus fn at x minus fm at c minus fn at c is equal to fm prime at y minus fn prime y times x minus c. Exactly the same argument as this thing here above. Now, if x is different from c, then the following holds. Right, all I did was to divide this equation here by x minus c, take the absolute value. But we know that this is less than epsilon over 3 whenever m is greater than n is greater than k, whenever x is in the interval I. Then we know that x is not equal to c because that's the way we've built it here. So now let m go to infinity. Fix n, let m go to infinity. What this is saying is that the limit m goes to infinity, the difference of differential quotient would be the same as the limit when m goes to infinity. This here is fx minus fc divided by x minus c minus fnx minus fnc divided by x minus c, an absolute value. And since each of these terms is strictly smaller than epsilon over 3, then in the limit, they cannot be larger than epsilon over 3 whenever n is greater than k and x is an I. So, when the distance between x and c greater than 0 but smaller than delta epsilon, x is in the interval AB, then the distance between f at x minus f at c divided by x minus c minus g at c, that is going to be equal to, and now we add a bunch of zeros, but we add them in very strategic ways, so that's fx minus f at c divided by x minus c minus fk x minus fk at c divided by x minus c plus fk at x minus fk at c divided by x minus c minus fk prime at c plus fk prime at c minus g at c. We've just added zeros. Triangle inequality, this is going to be less than or equal to f at x minus f at c, x minus c minus fkx plus fkc divided by x minus c plus fkx minus fkc divided x minus c minus fk prime at c plus fk prime at c minus g at c. We've said from previous slides, this first part is smaller than epsilon over 3. The second part is smaller than epsilon over 3. The third part is smaller than epsilon over 3 as well. One of those was exactly equal, or at least could have been smaller than or equal, but in the final analysis, when you add all of the three together, you get the difference between quotient fx minus fc divided by x minus c and the function gc can be made as small as possible if we pick x close enough to c, which means that f prime equal to g on the interval. Fairly involved proof that requires you to understand definition of the derivative, the definition Cauchy sequences, the definition and usage of the mean value theorem, more than one occasion, understanding what uniform convergence is. It is not obvious. Okay? This is a difficult proof.